Akhtar, so can we start?
Hello.
Yes, sir. Sir, can we start?
Yeah, sure.
Okay, sir. Okay, good afternoon to all the participants for the fifth session of the 5 days ATL workshop. We have with us Dr. Akhtar Rasool, sir. Good afternoon, sir. Uh, a brief introduction. Dr. Akhtar Rasool, sir, is currently working as an assistant professor in the Department of Computer Science and Engineering in Maulana Azad National Institute of Technology, Bhopal. He has more than 15 years of experience in teaching and research. His area of specialization includes string matching algorithms, parallel computing, artificial intelligence, big data analysis, and software engineering, and analysis and design of algorithms, cluster and grid computing. He has published more than 15 research papers in SCI and Scopus Index journals. He has organized more than 5 workshops and STTPs, and also he has attended more than 20 workshops and STTP events. He is currently a part of several administrative activities of the college. Over to you, sir.
Okay. Abha, you have taken my CV. That CV is approximately 10 years old, 11 to 10 years old. That's okay. I have published more than 80 publication in various SCI and Scopus Index journal as well as many in the conferences. Okay.
Okay, sir. Okay, sir.
And my specialization also in the quantum computing. Okay.
Okay, sir. Okay, sir.
So sorry, I'm not able to on my camera because of the bandwidth issue, because I am taking this lecture from my personal place. So uh, this is one more thing. I just wanted to add that uh, is I'm audible to all
Yes,
of
sir.
you? Okay.
Yes, sir.
So one thing is that I have many material to discuss. That's why I'm not going to prepare the PPT. So I'm preparing my notes and taking converted that note into PDF. So I'll discuss with the PDF. So because there are lots of parallel computing codes and APIs are there for discussion. That's why I'm just taking the PDF. So, if anybody having the queries uh, during the discussion, then please stop me and then ask on immediately on that particular point of time. Okay. So, I'm just sharing my screen. So, okay. Are you all able to see my screen? Abha?
Yes, sir.
Yeah. So I'm starting this lecture. So previously, this particular, I think this workshop is for the purpose of discussion of parallel computing, or you can say the high performance computing. So there are, in the high performance computing, there are many fields are there. In the big data nowadays is also a part of a high performance computing. Also, the you can say the quantum computing is also the part of uh, parallel computing, and many other the current issues are there, which is automatic a part of a high performance computing. So for doing high performance computing means computing on a high performance machine. So high performance machines, or you can say high performance machine, you can say a parallel computer. So what is parallel computer? So you can say parallel computers means the computer which are able to do the parallel processing, that called a parallel computer. Normally, you can say a large number of computers are connecting through a common channel or through a common LAN, high speed LAN. And that all computers working together and working for solving a particular objective, that is called the parallel computer. So computing on a parallel computer is called the parallel computing, and also some kinds of high performance computing. So whenever you have a parallel computer, means the computer various computers are there, and you have to combine that particular computers, set of a computer, and connected this through a high speed LAN. That is called the parallel computer. And for computing on that particular machine, you have to go for a parallel programming. You have to make a parallel program, and that particular program is going to be run on the machine, that particular parallel computer, and gives the high performance. So these are all our parallel computers, or these parallel computing, high performance computing is to be done on both kinds of job, a data intensive application, and a computational intensive application. On both kinds of problems, so this particular um, parallel computing is going to be used. Uh, if you talk about the parallel computing or parallel computers, you have to understand there are two basically kinds of parallel computers. There are a shared memory architecture machine, or a distributed memory architecture machine. So shared memory means a parallel computer. Nowadays, you all are using the machines. That machines are quad core machines, octa core machines. On a single computer is also nowadays a parallel computer, a small parallel computer. A workstation having multiple cores are there. GPU computing is also some kinds of parallel architecture. These all architecture, which are I'm discuss multi-core architecture. These are all architectures are basically a shared memory architecture. So on the shared memory architecture, there are you can generate the parallel processes to for which are going to be executed for solving a particular objective, for particular common objectives. Whenever a communication is required in the shared memory architecture, they are using the shared variables. Of course, when you are using the shared variables on a sharing on the shared memory, for to you have to take care about the problem of inconsistency in the copies of shared memories. That is one more common problem of cache coherence problems. then you have to take care of these problems. For that, you have to use critical sections and other synchronization mechanism to avoiding the inconsistency in the data. These are shared memory architecture basically used for the purpose of solving the data intense application, right? And this is also some kind of SIMD architecture, that is called single instruction multiple data kind of architecture. Uh, when you're talking about the distributed memory architecture, in the distributed memory architecture, this is important. It is important that the data is not going to be shared too much, because there are computers which are on a different places, and there are no shared memory kind of a concept. So whenever communication is required, you have to send the different computers or a process running on a particular computers send messages to other computers or other processes. So that kinds of called the message passing mechanism. So you can say the communication is to be established through the message passing mechanism. So when you're talking about the parallel programming, there are two kinds of programming. So shared memory based parallel programming, and the second one is distributed memory based programming. So for the shared memory programming, there is a framework called the OpenMP. So you can use the OpenMP for the purpose of doing the shared memory based parallel programming. For the distributed memory based programming, there is a library called the message passing interface, MPI, is going to be used. So today's lecture is about the MPI programming, how you program on the parallel machine using the MPI. Of course, that parallel machine is a distributed memory machine. So, this is just a brief introduction about the parallel computing. When you're talking about the MPI is basically applicable on distributed memory parallel architecture. This is actually a standard of message passing. So whenever you first when it is launched, it is just an standard or a communication protocol is to be written, and that standard is about of 852 pages. Afterwards, these this particular 852 pages is to be available on this www.mpiforum.org. So you can download this and you can easily study about the MPI. But nowadays it is not required, because that's many wrapper classes are there which uses the MPI, and more advanced framework are there inside that. MPI is playing a major roles. For example, CUDA. Sorry, for example, you can say languages like Hadoop, Spark, Kafka. So these all Apache Kafka. These all are uses inside that. There is a programming of MPI. So there are many concrete in the supercomputer. They are also use the MPI, but they customize that particular library, and so that MPI library is called the customized library of MPI for that particular uh, supercomputers. IBM MPI is also there. IBM supercomputer MPIs are also there, and more advanced versions of different supercomputer for MPI is also available. Uh, so they all are may customize this library for their own purposes. So some tasks are data intensive, and some tasks are complicated. means you can say there are lots of work to do, or the some problems are there where the complicated calculations are there. So MPI is basically for the complicated calculation. It is not means you can solve the various different NP hard problems using MPI, but it is not going to be solved for processing the big amount of data. Okay, so this is because this is a distributed memory architecture. But nowadays, the version like Hadoop and Spark also uses the MPI in a different shades that also used in the data intensive application. So when you're talking about the history, so the first version is coming in 1994 for the Fortran, and C bindings are there. Then there are some minor corrections in 1995. Then 1990, say more advanced features are there, and some communication mechanism is also going to be changed. One-sided communication, parallel input output, and there are C++ binding also there. Afterwards, after some years, C++ binding is to be deprecated in 2009. Um these MPIs are going to be having a two parts: a simple MPI, the basic MPI, and then go for a advanced MPI, where you go for a collective operation, synchronized mechanism, and many more advanced features are there in the MPI 2. Then the version 3 is released in 2012, and some more versions is to be come afterwards. In 2017, version 4.0 is also available for message passing interface. See, when you're talking about the MPI, it is for the distributed memory architecture. See this particular figure. Suppose these are the machine, one, two, three, four. These are the four machines. Inside that, there are multiple cores are there. So nowadays, machines, parallel computers are the combination of multiple processor. Inside a processor, there are multiple cores. So this is, you can say, a multiple processing elements are to be here available in the parallel computer. For this example, if suppose this is a single machine, inside that there are six particular cores are there. In that there are again six cores are there. Six cores means the six different processing elements are there, having, and each core having its own cache to process the data. So there are every computer, you can say, nowadays every computer quad core or multi quad core processor and many other core. These automatically are a small parallel computing machine. All right, parallel computer is there, but this is that particular parallel computer is not distributed memory. It's a shared memory because there is a common RAM is available for the processing. So suppose we are going to use this particular architecture for parallel computer. So MPI means different computers are connected through the high speed LAN. So MPI launches a program of the processes. This program is of having the multiple processes, and that process, every process are running on different computers. If you are allocating eight processes, so see, definitely there on this particular computer, two processes are going to be run. Two on this, two on this, and two on this. So how many parallel how you go for parallelize, how many processes is going to be used, that is up to you. How you going to parallelize a particular program, that customization is on you, how you parallelize this. So you have to make a program which is properly utilize this particular architecture. So different two processes running on this computer, two processes is going to running on this computer, and so on. When a process is running on different computers, they wanted to communicate each other. Then they have to send the messages. Then they have sent the messages to one to another. Let's say this process running on this computer wanted to share some information to this particular process. So this process is send the message through this network, and the message containing some sort of data. So data is not the huge data, but sharing some data. Just this is called a message. So communication between the process uh, is to be done through the messages. The MPI, the message passing library, the message passing interface library uses the SPMD architecture. So SPMD architecture is little different from SIMD architecture, because there is a SPMD means single program multiple data. It's not in the single instruction multiple data means the SIMD architecture. There is only a single instruction register, and there is only a single program counter, and that all the processes running the same instruction at the same time. Here, the single program multiple data means you have to make a program and then compile it, and you make executable of that particular program, and then share to the different machines available on the parallel computer. So see, when you share the executable on different machines, each machine having its own operating system, and it's having its own data on which they have to process. They have to go for processing. So this program is running on different machines, and after completing their processing, they have to combine their results. Afterwards, in between if they wanted to communicate each other, they have to send the message from one computer to another computer, and that is to be done through the message passing API. So here the program is going to be shared. So maybe there should be heterogeneous machines, means some machines having fast and some machines having a slow processing. So based on their processing capabilities, that program is going to be run. So no common instruction is to be executed on different machines. So program is going to be run according to their processing speed. And after completing the processing, they have sent the results for the result for the final solution. So this is a single program multiple data, and the data should be different, or because data on different machine there is a different data is going to be available. So that program, the basic architecture I'm just going to be discuss. So MPI is a concrete realization on SPMD architecture. There is suppose your program, so you have a parallel machine of four computers, right? Four computers up inside a particular computer there could be a multi-core, but we are not going to discuss that. How many processing elements are there. So sometimes programmers are aware of these kinds of uh, specification. If you are not aware of these kind of processing, you normally set that number of machines. So you have to, for the better processing, you have to allocate the number of processing equal to number of processes on the parallel program. So see, when suppose you have a four machines, and each machine, when you write a program, so inside the program, you have to write that there are four processes, parallel processes are running for completion of this particular common objective. And then in the program, the different the same copy of program is running on different computers. See, there are each computer having this MPI. MPI assign a particular process ID to each computers. For example, there are four processes MPI program launch. So a process running on a particular computer may be assigned 0 to 3 ranks. So there are unique ranks are allocated to the processes. So, for example, the first computer process rank or ID process ID is 0. The second one is ID 1. Third one is ID 2, and fourth one is ID 3. So there are four different IDs are there. There are four different IDs are there for the identification of the process running on different computers. So if you wanted to assign different tasks to different process, you write in inside, because this is a common program, so you have to write this kind of codes. If my id equal to this one, but the particular id is equal to 0, do this one. Particular id is equal to my process id equal to 1, do this one. So means different tasks are allocated to different processes. So this is also a realization of MIMD kind of a architecture. Multiple instructions, multiple data. So different datas are to be there, and definitely different tasks is to be performed by different processes running on different processes. So a common program is there, but how you allocate a particular work to a particular section, a particular computer, this is to be done by this kind of a code. If I'm writing this code on C, so my ID equal to specific ID, and do something. When you're talking about SPMD environment or a MPI environment, uh, the API is going to be associated with these kinds of activity. The first activity is provide identification of all participating processes. Okay, so पहले आपको क्या, you have to go for make an identification of our participating process. For this you have to make a use a particular API, which API assigns a particular process ID to a specific process. Afterward, the API to check whom to send the data, uh, how much data is going to be sent whenever your sending is required, what kinds of data is going to be sent, and if some data is arrive on your machine, so you have how you check that particular data, and accordingly how you allocate the buffers. Then if there is some kind of synchronization is required in the processes, then there should be a API sets to be available for the synchronization purpose, and how you launch and control the process. So these are the activities on which you have to go for use of this particular APIs. The agenda, when I'm just going to start the MPI programming, because this session is only for the MPI programming. First we discuss about how you start up your program when you are writing on MPI MPI environment, working on MPI environment. how you write a basic program. So you have to do a startup program, initialization of the variables and the finalization of the variables, and how you shut down the environment. In between, send and receive the messages, and what is the message and envelope, and the different kinds of communication, point to point communication. We are just going to discuss some basics data types. We are using different kinds of send and receive. Then there is a blocking and non-blocking operations. There is some kinds of modes, and then some basic mistakes which is going to be committed while writing the MP program. So see how much we can cover on this limited time. So I'm just going to discuss about the basic programming of MPI. Any questions till now? Hello, hello.
No, sir, no question, please.
Okay. So start with the MPI structure. Uh, so this is just simple C like programming. So for the startup, initialization, finalization, and shutdown, this is the basic program of the MPI. And in this particular program, whatever step I've written, these steps are must. You have to must write these statement for starting up the program. For example, first you have to add MPI.h. So MPI library you have to add. MPI library is available on different versions. So you have to install that particular MPI library. Okay, on your computers, and then afterwards you have to start writing the program. So for that hash include MPI.h. There is int main argument. This is similar to the C++. There is a MPI init with argument C and argument V. The count of the argument and the value of the argument. So MPI init and MPI finish. These are the two important words you have to write in the program of MPI. MPI init means initializing the MPI environment. So when you apply the MPI init function, then only you can go for writing the parallel program. And inside that, only parallel program is going to be written. So whatever written inside MPI init and MPI finalize, that is considered as a code, parallel code. These two APIs you have to write. There is some wrap-up functions. Afterward, you can, if you wanted to use some wrap-up functions. Wrap-up function means if you are allocating some memories or allocating some variables, so you have to wrap up or clean that particular memory using some wrap-up functions and return zero. So these are the basic program. Uh, See now this program. This program, suppose how many process are running on this particular program. So for that, see first this one. So first, whenever you write a program, MPI program, so you have to compile this one. So MPI CC all uh, executable is name of the executable, and then the program name, executable name, and then the program name. You have to write on these two things. This will give you the exe of exe. If this is going to be success, this will make an exe of this particular program, parallel program. And then MPICC, the number of processes, program, and then argument one. Based on that, suppose here you give the name of abc.exe. So MPI minus n, let's say 8, 8 abc.exe. Then you supply the argument. This is the number of processes. So this you have to give how many processes you are going to be run on this particular parallel computers. So this one you have to compile the program and then we are going to be executed. See this second program, each and every program is running on different machines. So process is running on different machines. For this, first you have to identify who I am. So for who I am means what is your rank. So there are eight programs are there, eight parallel programs or processes are running. Of course, ranks lies between 0 to 7. So what is my rank? Is each process having unique rank. So for knowing this one, you have to write this one hash include MPI.h, then int main argument C, argument V, and then MPI in it. This is must. Then write a parallel code. For writing this, for knowing how many processes are going to be run in this particular, so we have to supply 8 on the command line side. Means the 8 processes are running inside that. How you know that this 8 is supplied for the number of process for this MPI communication size. So MPI underscore com world, comma, the number of processes, comma, the number of processes. So this is going to be used. The number of processes variable you have to declare on the top of this MPI in it. Maybe you can initialize this inside a parallel code, but this the multiple variables are going to be used. Then on each variable is allocated on different machines. So this number of processes holds how many number of processor are going to be executed this particular code. So MPI com world comma at the rate number of processes. So number of processes. So we supplied 8 when we are 8 on the command line. So this number of processes integer variables holds the value 8. Okay. Now the second one is rank. Now you wanted to know what is my rank is. Rank means what is my IDs. IDs lies between 0 to 7 because 8 is supplied. So each processes wanted to know that what is my IDs. So MPI underscore com underscore rank, and then variable it declare is rank, and rank will hold the value of the parallel processing. So what is the rank? What is rank means? Rank means your identity in the parallel program. Then you start writing the parallel code, finalize it, and wrap up. So normally these two functions are used. So 3 4 functions are must. You have to must write these function MPI in it, MPI convert size. Then this will give you this value is to be held in a variable that is called the number of words. So eight is coming here. You should supplied 8 in the command line, and then MPI underscore com rank. So this will give a rank variable is there. This will hold the value of your rank. So there is suppose that you have a 8 machines. So process so one on any machines these are unique values is to be assigned to the processes lies between 0 to 7. Now, whenever you required, you have to send and receive the messages for parallel processing. Send and receive the messages, and inside the messages there's definitely a data. So I'm talking about the simple first. I'm talking about the simple send and receive. Suppose there are two processes, A and B. Of course, you can say that this ID having one or this is ID having zero. If this is send the data, and this particular process has to receive the data. For the sending code, to sending means there are certain MPI underscore send for sending information inside the process to you. How you write the particular send and receive for? If my rank equal to zero, I have to do this one. If my rank equal to one, I have to do this one. So for this kind of a section will give you the separate task of execution in the parallel programming code. So MPI underscore send means void data. The argument is data. So whatever data you wanted to send, you have to supply the pointer of that particular data. Then the count. So importantly, here we have to send a block of data. We're not going to send the non-contiguous memory allocation or a tree. So you have to send a array, or you can say continuous memory allocation. So suppose you have to send the data of four. The four block data is going to be shared. For that, you have to supply the data and then the count of that particular data to be sent, then the data type, which type of this particular data which are going to be sent, the type of data, and then the destination, integer destination. So your rank of the destination is to be assigned, and then the tag, integer tag means identification of message. If one process is sending several message to other process, how we identify which send is equivalent to which receive? For that, this send and receive send destination, uh, this tag is to be assigned based on your destination rank. And then the communication world or environmental MPI environmental word. So tag is lies between 0 to 32767. Okay. Rank, you know that the lies between 0 to n 0 to n minus of 1. Uh, this is simple sen. When some process is going to send a data, a different some other process is going to receive that particular data. For that particular process going is waiting for the data. So for collection of data, there is API MPI underscore receive for RECV receive. Here again, data which a blank data which are going to be hold the data of sender, and then integer count of the data, then MPI type, the same type of data is going to be received, then tags. If same type of data is not there, the second machine will reject the data. Then integer source, integer tag, and the com world and status. So what is what is data types? Data types, for data says MPI underscore char for the characters, MPI underscore short for short, MPI underscore int for the integer, MPI underscore float for float variables, MPI underscore double for double variables, MPI underscore unsigned character for unsigned characters. This is, I'm just going to discuss some example over there. See here. Suppose two processes are running on different machines, different machines, and on two machines are there. So one is sending one rank is zero, and second the process rank is zero, and second is process rank of one, right? So rank one process sends the data to rank zero. So same program, same program having two different sections. If my rank equal to zero, then you have to launch a API MPI underscore receive of this kind, this particular information. Whereas if after ending this, my rank equal to one, sorry zero, after my rank equal to one, I have to send the information. You have to write the sender code, MPI underscore send. So this is sending some data. So sending a variable b. So I'm passing address b. Uh, how many data you this particular rank send? One variable, one data of what? Integer type, MPI integer type, and the tag of this the rank. Which rank you have to send? Zero. Yeah, the MPI underscore int zero. So zero rank data you have to send the information to zero rank process, and then the tag of the data. This tag is basically for identification of the messages. Suppose rank 1 sending hundreds of message to rank 0. How you identify which send is equal to which receive? So for each send there should be a matching receive, and this matching receive is to be done by sending the common tags. So this tags, when these tags are going to be matched, then you are saying that for this particular send there is a receive. So on the receiver side there is another variable you have to declare a, which holds this information send, which are holding by b, of one size MPI int 1, or of course tag 0. Here receive is launched for receiving the value from the rank 1, and we are here the rank of 0 where you have to send, and this is what where this data is coming from. And then MPI underscore com world, this is for communication world. So this is the purpose of writing a simple code. I'm just more elaborating this code. See over here. So you have to write hash include MPI. So you have to write these all things: number of process, rank, data, MPI status, and status. This API is also uses the status, which I'm discussing later on. Right? So this one is MPI init. So you write MPI init for parallel programming. Afterwards, you have to write MPI underscore communication size. So com world means the environment. You have to set the in this environment how many processes are there. So you have to launch a variable is number of process. So this variable, after execution of this API, this variable holds the number of processes. So that number of process you have to write this if else sections. If it is not zero, if it is not one, then You have to write this code. So in the previous example, I'm sending a 0 are the receiver and 1 is going to be sender. So if by rank equal to 0, MPI underscore receive is to be launched as the data 1 MPI init 10 forward status. This I'm just going to discuss. This status is one variable which holds the this API status receive. Okay, MPI underscore success. This will give when this particular receive is going to be completed. If you have to send the a large amount of data, then the data is going to be sent in the various parts, and after receiving all the parts and combining that all the parts, then only this message is going to be MPI underscore success. Otherwise it will give you the status. So this is receive. Else if rank equal to 0 is equals to 1, so MPI underscore send, इसमें ये आपको send की information लिखनी पड़ेगी. So you have to send all the information. Then the MPI finalize. So for the better understanding, you have to declare this here. You have to declare some variables. Uh, let's say A and B or data. So data equal to 10 and then 10 is going to be sent after the receiving. Then you finalize the code, return to 0, and then close the Perl program. Whenever a send and receive is to be done, whenever a send and receive to be done, a send and receive is to be done by matching an envelopes. This is called the message envelope. So message envelope uh, having some fields. So send for each send there should be a receive. Okay, for each send there should be a receive. So whenever you are writing a program, you have to check that number of sends receive is equal number of sends equal to the number of receives. Then your program is going to be correct. For each send and receive, there is the data is to be transferred by checking the envelope. This message envelope having fields, source and destination. So this information is to be done in the this message envelope. Then tag. I'm saying the tag for the identification of the send and receive. So unique tag is to be assigned uh, for 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 the uh, purpose of send and receive. So tag values are lying between 0 to 32767. Okay, this much number of tags send. This much number of sends is to be used in a single programs. And afterwards, the communicator is there. So which communicator means on which environment this parallel program is going to be executed. So each send is receive valid for the particular environment, particular send and receive. This API is going to be failed on these conditions. If send count is less than equal to receive count, means up you have a send buffer, you have a receive buffer. So if you have a um, huge data of receiving, means let's say you have to send 10 elements and the receiver having a buffer of 12, so the easily this send is used is to be copied in the different buffers. This of course these send buffer and receive buffers on different machines. So if send count is less than equal to the receive count, this is okay. If send count is greater, means you have to send 100 bytes, but the receiver buffer is having only 19 bytes or 90 bytes. So this is not going to be success. This API is not going to be successful, or this will not process the data. Whenever a send and receive is to be launched, the status is you have to pass a MPI underscore status. So this will give you the information about the MPI underscore success. Sometimes MPI underscore source भी बता सकते हैं आप कि source इसमें क्या है. MPI underscore tag for matching the envelope. MPI underscore error. If some errors are there, then this will give you the error code. So you have to trace out what kind of error is going to be processed. And then one more is MPI underscore success for successful completion of the MPI code. Whenever you launch a send, the program send or receive in a program, your program will halt until unless send or receive is going to be completed. After completion of send and receive, then your program is moved forward. For checking the status, of the send and receive, so you have to use the MPI underscore probe. So MPI underscore probe, what it sends the sender tag of the message, and then the communication world, and it sends the status matches which is used in send or receive. So status जिस भी send और receive का status आप इसमें pass करेंगे, that particular status give the information about that particular send and receive. So after applying this API, this status holds the information about that that is about that particular send or receive message. If you are this will not give you, if you don't give the success, this will maybe give you, this status is really give you in progress, or send or receive is in progress, or some more messages are there. If it will give no receive is there, so you have to launch the particular receive for this particular send. So this is very important. API is MPI probe. The next API is for the MPI get count. This MPI underscore get count give the count of the message. Okay, how much memory this particular message is holds. So I'm just discussing now the message passing deadlocks. For that, please wait a minute. In the MPI programming, all sends and receives, normal sends and receives are able to create the deadlocks. How this will create? See, if rank wanted to send the information uh, to 1, and rank 0 sends the information to 1, and rank 1 is sent the information to rank 0, as see in this particular figure. uh, Rank 0 sends the data to 1, and rank 1 sends to 0. This send is going to be completed when this send receives the matching matching MPI receive, and this send is going to be completed when this will receives the matching receive of this particular send. So combination of send and receive is to be there. Then only this API is to be completed. So this send is waiting for a receive. Then only this receive is to be launched. And this send is also waiting for a receive. When uh, waiting for a receive, then this is going to be completed. So both this and this are waiting for receives, not going to be completed. But this receive is only launched after this one, and this receive is also launched after this one. This will create a deadlock situations, right? This will create the deadlock situation. So sometimes see, whenever you're writing MPI program and you're writing MPI send and receive, you have to very careful about very careful about uh, is there a situation of is there a situation of deadlock or not. So communication is to be done fast, and then each communication at a time, only one communication you have to establish between the two processes. So let's say 0 wants us to send the communication to 1. So first 0 let finish their communication, then rank 1 should start their communication. So the better way to handle this deadlock, so careful about the writing the program in this way. So first let's say this rank 1 sends the data. So rank 1 communication should be completed. So this communication is to be completed only when only when this sends receive a matching receive. So you have to rank 1 first launch the matching receive of this particular send, right? Matching receive of this particular send. Afterward, it launches the send of 1, means their communication. And then this rank 1 launches their own receive, matching receive of 0. So be careful about writing the program. In the program, if you'll see, so you have to write the program in a way like this. If my rank equal to 0, receive MPI receive that message from coming from the destiny from the source 1, and then MPI send the message to 1. If my rank equal to 1, I have to first send the message to 0, means the destination is 0, and then receive the message from 0. So this combination is to be there. So whenever two processes are going to be communicating each other, you said that the communication, let first communication is finished, then go for a second communication. Don't launch a multiple communication together. So that if you launch this one, these are all are deadlocks, because if one communication is completed, then only the second communication will be launched. To avoid these deadlocks in the MPI program, you can use the combined MPI sends and receives. Right? There is another API, MPI sends and receives. So this is to see all the arguments are going to be combined. Send data, send counts, MPI data type, destination tag, and receive. The other one, receive data, receive count. Of course, send count equal to receive count, and then MPI data type, MPI data type, this send type is equal to the receive type, and then source. This is a source, and this is destination, and then tags are going to be send tag equal to the receive tag. There is the MPI common environments are there, and one single status is MPI status. So see, you can avoid by launching a combined MPI send and receive. You are easily going to be avoiding the deadlocks. But this MPI sends and receives are very slow API, because this is a combination of both sends and receives. So there are multiple more communication handshaking is required between the two processes. Because of additional handshaking, this API is going to be slow. So we are going working on a high performance computer. If your APIs are automatically slow down the process, this will hurt your overall processing. So for avoiding this, you avoiding this, you are not using this one. But if in some cases, you can use this send and receive also. Now, for better programming skills, so let's see. MPI programming is only passes programming is only for sending and receiving the messages. Okay, so that's why I'm focusing on how sends and receives are working. Is sending and receiving the messages. You have to make a non-blocking API, or there's no deadlock APIs. For this, a new set of APIs is going to be used. That API is going to be used name of MPI send. Okay. Instead of MPI send, we can use MPI send. So MPI send is a non-blocking API. So what this API is going to do, this after launching the send, it gives the control to the program. It's not going into the deadlock until the receive is to become. So all MPI underscore I I I APIs, I send, I receive, these all are non-blocking APIs. All arguments are going to be same. Instead of one argument, there is a MPI underscore status. Here MPI underscore request. So how you know this one? See this one. The sender can easily MPI underscore send, and receiver easily MPI underscore receive, and then start doing another processing. How you check this particular send receive is going to be complete or not? For that, you have to use MPI underscore wait. MPI underscore wait function, see, uses this request and then status. This request function, when you passes into the MPI underscore wait, so this request function checks whether this particular request is going to be completed or not. Okay, if it is going to be completed, this then this MPI underscore wait will not halt, and then passes on to the control to the program. So what is the process of writing this one? First, correct of launching this one without thinking of completion of the programs, completion of the communication. You have to launch MPI underscore receive first. So receive is API is going to be completed, is to be launched, and its request is there until he got that particular statement is MPI underscore receives send message, respective send message, then only it is going to be completed. So when you launch MPI underscore I receive, it gives the control to the program. Again, this is launch and waiting for matching send. This is again launch waiting for matching send. Now you launch MPI underscore send. So then this send is information is there. and then when it receives the proper send message, and this is give the success, and it is also give the success. You have to check whether this particular send and receive are complete. You can use MPI underscore wait. So see, in the here you launch this one, do some other work, and after some time you are able to check whether this send is going to be completed or not. So this send is only going to be completed when matching receive is there. So here matching receive, whenever he got the matching receive in the program, so after the execution of this particular section, this will going to be completed, and this receive is also going to be completed, and the status of that particular send and receive is going to check by MPI underscore wait. One more function is there, MPI underscore test. This is for testing whether this particular send or receive is going to be completed or not. Means this request is completed or not. This is flag, okay, and this is for status. So this flag will give you a value 0 and 1. Oh, okay. So based on these integer values, based on these integer values, there is a coding of this MPI test. Based on that, you can identify that this particular send and receive request on which position. For all waiting, for multiple operation, for all waiting, all test, wait for all, wait for all, and wait for test all. Means all sends and receive for all processes. Here we MPI for wait all. Okay, so waiting for all completion of all the sends and receive. Then you stopping the program, and then start combining the results. For that purpose, this API is used. And then wait for any. Similarly for the wait for any, and similarly for the MPI underscore testing. This is for the simple send and receive. So for the normal programming, you have to use MPI send, MPI receive. For non-blocking APIs, you can use MPI I send, MPI I receive. For whenever you are using MPI I send, I receive, you do not need to thinking about the communication, how communication is to be done. You can easily launch the APIs. For checking the APIs of non-blocking API, you can use MPI underscore wait, and wait is to be checked by the request function. Wait having different shades, wait for all, wait for any, and this will give you the status of all the requests, or check the status of any particular request. Now special operations, some of the special operations are there in the MPI programming. These are called as the collective operations. Collective operations means all the processes are participating in these APIs. All the you can say all the ranks, processes or ranks are participating in the programs. So whenever these APIs are used, all the process has to be participating. So MPI barrier is for stopping the processes on a particular location. So MPI underscore barrier. So barrier is there. Barrier is barrier is based on, you have to slow down the processes and make the processes all the processes are uh, all the processes are to be executed on or synchronized at particular time. So yeah, here you have to give the barriers, MPI barriers. It means that it is not like that the zero rank zero completed all its task and other processes are not going to complete their task. So all the processes are going to be running, right? So this is called the barriers. So all the processes should be completed on the same time. All you can say at any point of the time, all the processes are going to be executed, and you're checking the status of the program. Suppose there are 15 instructions in the program, 15 instruction of the program. You can put the barriers to 5. So there are maximum 5 instructions variation in each processes. Means one process is running on 9, then all other processes, maximum process is running 9 instructions. Then the all other processes maybe on 6, 7, 8. It is not like that if one process is running on 9 state instruction and other processes are running the first statement. So there are barrier of 2 3 statements, 2 3 instructions are there, 2 3 send and receive operations. This will give you some kind of synchronization or barriers in the programs. So this will give you the time slot of using the barriers. I'm just giving the idea of how you can synchronize the different processes. Okay. So this is the second for the broadcasting purpose. If you wanted to broadcast a message to all the process, then you can use the MPI broadcast message, bcast method. If suppose I wanted to write a program, I'm writing a program for broadcast the message. To see what you do. Suppose a root node is there. Zero is the root node, and there are 10 processes are there. So you have to send the information to 10 other processes, 10 other processes. Then you have to take care about. You have to write this program. Here, see what you do. If my rank equal to 0, I have to send the information to other 9 processes. So if it is not equal to root, then MPI sends. So 9 cents are used. MPI 9 cents are used each time you are using a different destination. So suppose our node is going to send the information to all other participating process. Instead of writing this kind of a code, you have to and another process is launching the receive. You have to use the bcast. The simple bcast. Bcast means data. This is the root node which are going to be broadcast the message. This is in count, the number of data you have to send, data types, and communication. So all processes uses the MPI broadcast means or this A. If some data is on route A process, so this will automatically broadcast to all the information. So sometimes whenever you start the process प्रोसेसिंग तो आपको जो इनिशियलाइजेशन का डेटा है वो आपको सब सब प्रोसेस को देना होता है फॉर द इनिशियल प्रोसेसिंग so that data you can easily broadcast through the bcast method. Otherwise you have to launches many sends and receives for sending the information. Scattering, if you wanted to scatter the data, suppose this is rank, this is the data on rank 0, this is 0 1 2 3. So this is going to be you are going to be scattered that data. So if suppose you wanted to do a some kind of a SIMD work in a single instruction multiple data, means you have to divide the data and on same instruction is going to be executed on different pieces of data. So the root node loads the data, and then scattered according to the number of process. So how this is it? This is what the send buffer, and you have to talk about the receive buffer and the receive count. So send buffer may be of, let's say, this is of 200, let's say. So A, B, C all are of 50 bytes. So you have to send buffer is of 200, receive buffer is of 5, and you have to launch this particular data scattered. So all 50 can 50 50 50 50 elements are divided and gives to the different processor for processing. So data parallel activity should be done on using the or through can be done through the MPI by using the data scattered API. So this is called the MPI underscore scattered. Similarly for the gathering, different datas are there. Then you have to send buffer equal to receive buffer. So uh, uh, send buffer is the smaller buffers, and the receive buffer is a large buffer which holds the information of the send buffer informations. Let's say send buffer having 10 elements. So there are 10 processes are there, the 10 into 10. This receive buffer is of a 100. So you have to gather information on a particular node. This MPI underscore gather is to be used. Then MPI all gather. This is a combination of just MPI gather and MPI broadcast. Okay, so this is called MPI all gather. This 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 is faster than these two combination API. So MPI gather means gather on a particular location and then broadcast it. तो जीरो पे आपने जैसे इसको किया है, उसके बाद आपने इसको ब्रॉडकास्ट कर दिया. So MPI this gather is used. MPI all to this is a combination of scattering and then gathering. So you have to divide the data, and then afterward you have to parallelize the data. Okay. And MPI reduce is there. This is very important. Reduce, and this reduces for the similar as a Hadoop MPI reduce reducers. So MPI underscore reduce, so it means you are combining the results. So send buffers, receive buffers, send buffers, receive buffers. So reduce on a particular location. So the root node is rank of a root where the reduce operation is to be executed. All now have to send the data. All have to send the data. And what kind of operation is performed in the data is to be defined in the MPI underscore OP operations, right? So these operations are MPI underscore max, min, sum. This is called product, logical and bitwise and the logical or, right? MPI reduce all for all the places it is going to be reduced. For all the process places it is going to be reduced. Apart from that, there are many other collective operations are there. For collective operations for the variable lengths. I'm just discussing for the equal length, you know? So if each having a different lengths, so you can use MPI underscore variable length. So instead of a number of variable length number, means the send or receive buffer में जो आप नंबर देते हैं वहां पे आप उस नंबर की जगह एक वेक्टर पास कर देते हैं. तो जैसे आपके 10 एलिमेंट है तो 10 प्रोसेसेस है, तो वेक्टर पास करेंगे जिसमें हर एक लोकेशन पे करस्पॉन्डिंग लोकेशन पे कितनी वेरिएबल कितना डेटा वहां पे गैदर होगा या कितना होगा उस उतने नंबर ऑफ काउंट लिखा रहता है. तो इंस्टेड ऑफ नंबर यू हैव टू पास अ वेक्टर, then gather all reduce, these are same. Reduce scatter block, These are the some kind of again a reduction operation. So actually, this is a very fast session because we have to finish this basics on NPI programming in a similar small 1.5 hour session. So I'm not taking so many examples over there. Maybe I wanted to include the many programs, but due to lack of time, I'm not able to include the programs. Just like a parallel sorting, the kind of see many other programs you can use for this. लेट्स से फॉर एग्जांपल ऑफ अभी मैं आपको यही बता देता हूँ पैरेलल सॉर्टिंग अगर आप करना चाहते हैं क्विक सॉर्ट करना चाहते हैं लेट्स से कैसे करेंगे आप डेटा ले लें ठीक है आपके पास एक रूट नोड है रूट नोड पे आपने प्रोसेस लिया यू हैव टू लोड द डेटा ऑन अ रूट नोड आपने वो अरे जो था उस अरे को आपने क्विक सॉर्ट का जो अरे है उसको रूट नोड पे लोड कर लिया आफ्टर लोडिंग द डेटा ऑन रूट नोड you have to broadcast that data to all the available process. So how many process your launches? You have to launches the number of the size of array. Let's say size of array है आपका 20. Let's say for a small number है 20 है तो आप 20 processes launch कर दे 20 process को आपने सेम अरे आपने ब्रॉडकास्ट कर दिया आफ्टर ब्रॉडकास्टिंग नाउ ईच बेस्ड ऑन देयर रैंक बिकॉज ईच प्रोसेस को कोई रैंक मिला हुआ है किसी को रैंक 0 मिला है किसी को 2 मिला है तो यूनिक रैंक मिला हुआ है तो हर जैसे क्विक सॉर्ट में ये होता है कि आप जब भी जिसको पिवट मानते हैं जब आप वो एंटायर प्रोसेस करते हैं तो पिवट इज ऑन हिज प्रॉपर लोकेशन पे वो आ जाता है उस एंटायर क्विक सॉर्ट की प्रोसेस के बाद तो आप हर एक प्रोसेस पे क्विक सॉर्ट एल्गोरिथम लगा दे pivot is different pivot is going to be different based on the rank तो हर 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 प्रोसेस हर प्रोसेस अपनी रैंक वाले लोकेशन के एलिमेंट्स को उसकी सही लोकेशन पे ले आएगी afterwards you have to start gathering the information and then that this is the result of the quick sort तो हर प्रोसेस अपनी लोकेशन को सॉर्ट कर देगी अब उसकी उस एलिमेंट को उसकी प्रॉपर लोकेशन बता देगी आफ्टरवर्ड यू हैव टू स्टार्ट गैदरिंग द इंफॉर्मेशन एंड देन जो गैदर्ड इंफॉर्मेशन होगी उसके हिसाब से आप अरे को प्लेस कर दें दिस इज नॉट द पैरेलल सॉर्टिंग अब ये तो छोटा सा है अगर आपको बहुत बड़ा प्रोग्राम है लेट से बहुत बड़ा अरे है 1 करोड़ 1 लाख एलिमेंट है या 10 लाख एलिमेंट्स है 10 लाख प्रोसेसेस आप लॉन्च कर दें अब कंफ्यूजन ये है कि 10 लाख प्रोसेसेस आप लॉन्च करेंगे इतना बड़ा पैरेलल कंप्यूटर है क्या आपके पास तो डोंट वरी अबाउट दैट इट मींस दैट एट अ टाइम मैक्सिमम लेट्स से कि आपकी मैक्सिमम आपके पैरेलल कंप्यूटर पे 100 प्रोसेसेस लॉन्च होती हैं तो एक बार में 100 ही प्रोसेस लॉन्च होंगी और जब वो 100 प्रोसेस लॉन्च हो जाएंगी आफ्टर कंप्लीशन नई 100 लॉन्च होंगी मतलब जैसे जैसे प्रोसेस खत्म होती जाएंगी नई नई प्रोसेस लॉन्च होती जाएंगी और सारी जैसे 10,000 10 lakhs आपके एलिमेंट्स है तो उतनी प्रोसेस लॉन्च होगी उतने रिजल्ट्स आएंगे सो एट मैक्सिमम ऑफ पैरेललिज्म आपको मिल जाएगा और उतनी प्रोसेसेस लॉन्च होके फिर आप कंबाइन करेंगे तो लॉजिक जो भी आप सोचेंगे नंबर ऑफ प्रोसेसेस के हिसाब से आप उसको सोचते हैं ना कि आपकी कैपेसिटी के हिसाब से कैपेसिटी अपने आप ही रिशेड्यूल्ड हो जाती है पैरेलल प्रोग्रामिंग में उसको हमको टेक केयर करने की जरूरत नहीं होती है तो दिस इज ऑल अबाउट द एमपीआई प्रोग्रामिंग इफ एनी doubts are there then please ask me the questions हेलो हेलो
Yes, sir.
हाँ प्रगति बताया मैं
Sir, saying something?
आई एम आस्किंग, किसी को कोई क्वेश्चंस हैं तो पूछ सकता है.
Uh-huh. Participants, if you have any doubts, please ask.
No, ma'am, everything is fine. Very nice session, sir.
ओके, थैंक यू. सो मैं अभी सेशन बंद कर रहा हूँ. Approximately 2:30, 2:35 we start again a new session, जिसमें मैं आपको थोड़ा सा ओपन एमपी के बारे में भी बताऊंगा, क्योंकि मैंने आपको डिस्ट्रीब्यूटेड मेमोरी के बारे में तो बता दिया. थोड़ा सा ओपन एमपी के बारे में भी मैं आपसे डिस्कस करूंगा चीज़ें. ओके, तो थैंक यू फॉर दिस सेशन.
Thank you, sir.
थैंक
Thank you,
यू.
sir, for the wonderful session.
थैंक यू.